In Lesson 3.6, Proportional and Non-Proportional Relationships, you will be writing equations for proportional relationships and non-proportional relationships. A relationship is proportional if its equation is in the form y equals kx. You may remember this form from Lesson 3.4 when we talked about direct variations. The graph of a proportional relationship will always pass through 0, 0, and the ratio of y to x is constant when x is not equal to 0. An example I like to use for a proportional relationship is buying pizzas from Little Caesars. It doesn't matter how many pizzas you buy, the cost is always going to be $5 per pizza. If you are to buy 0 pizzas, it's going to cost $0. If you buy 1 pizza, it's going to cost $5. 2 pizzas will cost $10. 3 pizzas will cost $15. Now, if I wanted to graph this situation, purchasing 0 pizzas is $0. 1 pizza is $5. 2 pizzas is $10. 3 pizzas is $15. And if I were to continue, it would be in a straight line going up $5 every time. Now, I'm not going to connect these because we wouldn't buy parts of a pizza. We'd only buy whole pizzas. But you'll notice it is in a straight line and it goes through 0, 0. If I were to write an equation for this situation, the cost of the pizza, or y, is going to equal $5 times the number of pizzas. If you didn't know that just from the problem, you could look at the table and figure out the rate of change. The change from here to here is 5, and from here to here is 1. Remember, the rate of change or the slope is the change in the y over the change in the x. So 5 over 1, or in this case, just 5. This is in the form y equals kx. So it's a direct variation. It's also a proportional relationship. The cost per pizza is always $5. If I were to look at the ratio of y to x, I'm looking right here. Y to x, I have 5 over 1, 10 over 2, and 15 over 3. All 3 of these are equal. Therefore, that's another way to tell it's a proportional relationship, because the ratio of y compared to x is going to be constant, or the same thing, except for when x equals 0. That's how you can tell from a table. Looking at a graph, though, the quickest way to tell it's proportional is that it's a straight line going through 0, 0. Now let's pretend that they start a delivery service and it's going to be a $3 delivery fee. If you ordered 0 pizzas but wanted the cute delivery person to come out and visit to say hello, that's going to cost you $3. If you got 1 pizza, it's going to be $5 for the pizza plus $3 for the delivery. That's going to be a total of $8. 2 pizzas would be 2 times 5, or $10 for the pizza plus $3 for the delivery fee, for a total of $13. If you ordered 3 pizzas, that would be 3 times $5, or $15, plus 3 for the delivery, which is 18. Now, if I were to graph that, 0, 3, it's going to be about right there. 1, 8 is going to be about right there. 2, 13, about there. And 3, 18 is about right there. You'll notice it is still in a straight line because it's still going up at a constant rate. It's going up $5 every time. But because of that delivery fee, the whole line is shifted up $3. $5. It starts at 3. This is not a proportional relationship because it doesn't go through 0, 0. If I were to write an equation for this situation, the cost for the pizzas is going to equal $5 times the number of pizzas plus the $3 delivery fee. Notice also, if you were to compare the ratios of y to x, except for when x is 0, if I were to compare these, the cost per pizza is not constant because 8 over 1, $8 for one pizza, that's going to be $8 per pizza. And then here, it's $13 for two pizzas. $13 for two pizzas means it's going to be $6.50 per pizza. These two things are not equal, so it's not a constant ratio between y and x, or the price per pizza changes depending on the number of pizzas you buy because that $3 delivery fee is getting split up over each pizza. All right, let's take a look at another proportional relationship example. A professional soccer team is donating money to a local charity for each goal they score. So for one goal, $75 donation, two goals, $150, three, $225, and so on. If we were to go and graph this data, it would look like this. Notice it's going up at a constant rate of $75 for each goal. You could find that out by doing the change in the y over the change in the x. And it goes through 0, 0 because for 0 goals, there's 0 donations. So this right here would be an example of a proportional relationship. What we want to do is write an equation to describe this data. The donation amount is going to equal $75 times the number of goals. If you didn't know that, you could figure that out by going like this from 75 to 150. That rate of or that change is 75. And from 1 to 2 is 1. And if you were to continue to do that through this table, you would notice that there was a constant rate of change of 75 over 1, or 75. So in the equation, that 75 is going to be in front of the x, or it's going to be the coefficient of x. Y equals 75x. Now the next question says, how much money will be donated for 12 goals? To figure that out, we would want to plug in 12 for x, or the number of goals. So we would get y equals 75 times 12. So y is going to equal 75 times 12, and 75 times 12 is $900. $900 will be donated for 12 goals. Next, we have a non-proportional relationship. Write an equation in function notation for the graph. So here we have the graph. And to be able to come up with an equation for this graph, it might be helpful to take the points on the graph and make a table. So here's a table of our x and y values. When x is 1, y is 9. You see that right there. And when x is 2, y is 12, and so on. Once you make it into a table, you can look at that table and see that the rate of change is 3 over 1, or 3. Once we know the rate of change, we can put that in front of x, because that's what it's changing by as we move 1 unit to the right. So that's what number goes in front of x to be multiplied by. However, if I just take x and multiply it by 3, 1 times 3 is only 3, and I need to get 9. If I put in 2, 3 times 2 is 6, and I need to get 12. If you look over in this table, you'll see what I'm talking about. 1 times 3 is just 3, 2 times 3 is 6, 3 times 3 is 9, 4 times 3 is 12. Those aren't the numbers I'm looking for. I'm looking for these numbers right here. So what I need to do to go from 3 to 9 and from 6 to 12 and from 9 to 15 and 12 to 18, I need to add 6 more after I multiply by 3. So our equation is going to be 3x plus 6. Now, your textbook doesn't want to tell you this yet, but I'm going to point it out anyway. Right here, this number right here is the same thing as the y-intercept. That's where it crosses the y-axis. Basically, if I were to, let me make a line over the top of this. If I were to take this line and move it down here like this, that would be the equation y equals 3x. But I'm taking it and I'm shifting it up. I'm shifting that line up 6 units. So that's why we have to add 6. So we take the y equals 3x and we add 6 to it because it's moved up 6 units. It's crossing the y-axis at 6. So basically, what might be helpful for you when trying to write the equation from a graph is you're going to want to basically fill in these 2 blanks. And you might want to make sure you get this in your notes. This right here is the rate of change, or the slope of the line. And this right here is the y-intercept, or where it crosses the y-axis. We will talk a lot more about this right here in chapter 4. But for now, like I said, just think of it this way. The rate of change is 3. So here's my line of y equals 3x, but it's been shifted up 6 units, so we have to add 6 to it. All right, we got a few to try on your own. I'm going to put this down so you can see this. Actually, I'm not, because it won't fit. Write an equation in function notation for the relation shown in the table. Well, if I want to write an equation, I need to figure out the rate of change. From here to here, it goes down 1, as this goes up 1. From here to here, it goes down 1, as this goes up 1. Remember, rate of change is the change in the y's over the change in the x's. So in this particular problem, I can tell by looking at it, it's going to be a linear function because it's a constant rate of change, and that constant rate of change, or the slope in other words, is -1. So I know it's going to look like this, -1x or just -x. But now I have to see if there's anything else I need to do other than multiply by -1. 1 times -1 is -1, but I need 3. So to get from -1 to 3, I need to add 4. I have a feeling that's what my equation is going to look like, but I'm going to go test it out with the other points to make sure. Negative 1 times 2, like if I plug 2 in here, negative 1 times 2 is negative 2, but to get it to equal 2, I have to add 4 to it. Same thing goes with this one. If I plug in 3 for x, negative 1 times 3 is negative 3, but to get it to be 1, I have to add 4. So I'm pretty confident that that right there is my equation, but it asks for it in function notation, or what I sometimes call fancy Nancy notation, you know, the fancy way of writing this equation. Instead of y equals, we're going to write f of x equals, and then negative 1x, or simply negative x, plus 4. I'm going to let you in on another little hint here. Remember when we were writing our equations for arithmetic sequences? We went backwards to the 0 term, or when x was 0. If I did that in this table, if I went backwards to 0, this number right here would be a 4. So when x is 0, y is 4. And what do you know? That's what we have right here, just like when we were doing arithmetic sequences. All right, we're almost done. 2 more quick examples. Here we have 2 lines on a graph, and we need to write an equation in function notation. You could go and make a table from your graph and do like we did up here, or you can do what I said up here and just look for the slope and the y-intercept. If I look for the slope and the y-intercept, this, remember, is the slope, and this is the y-intercept. The slope of this line, I'm going to look for 2 nice points on the line where they cross perfectly on the grid lines. This slope is 2 over 1. Remember, rise over run. You rise 2, run 1. So the slope is 2 over 1, or just 2. And the y-intercept, this crosses the y-axis at 1, 2, 3, 4, negative 4. So it's 2x plus negative 4. But since it wants it in function notation, instead of y, we'll write f of x equals 2x. And then you could do plus negative 4, but a better way to write plus negative 4 is just simply minus 4. Now keep in mind that this really is the same thing as having this line if I were to graph just y equals 2x, it would look like this. That's like the direct variation, or y equals 2x, but it's been shifted down 4 units. That's why we have to do minus 4. All right, last example. Y equals, we need to fill in the rate of change or the slope, and then we have to also fill in where it crosses the y-axis, or where it was shifted to. You want to be careful on figuring out the slope here, because this is not going by 1s, it's going by 2s. So to go from here to here, it's going from 1 up to 4. So it's rising 3 and running 1. So the rate of change is 3 over 1, or just 3. And the y-intercept is right here. The y-intercept is at negative 2. So in function notation, that's f of x equals 3x. And then instead of plus a negative 2, I'm just going to write minus 2. Again, another way to think of this is the direct variation equation of y equals 3x. But then we shifted it down 2 units. That's why we had to have minus 2.